So it turns out that what you can actually show, and this is a statement which is related to precisely this aspect. So you can actually show that. Well, here's the observer being torn apart. Okay, so that's the phenomenon. So you can actually capture this phenomenon without talking about observers, explicitly, introducing the notion of an observer as a stick figure, etc. It's sort of complicated. So you can actually talk about this without even mentioning observers. So the way to say this is you can say the following: that the metric itself is inextendable beyond r equals 0, not only as a twice differentiable metric, that's essentially the statement that there's a curvature singularity, but actually simply as a continuous metric. Being inextendable with a continuous metric, you should always remember this is really saying that observers are torn apart. Being inextendable as a C2 metric is the statement that observers measure at an instant infinite curvature. Okay. So the second statement is actually
why can't you measure discontinuity? I mean,
well, but this is sort of this is what it means. And actually, this is a much harder statement to prove, and it was only, even though it's sort of, that's what you think of it as a classic statement about the geometry of this explicit solution, it was only proven 2 or 3 years ago by Jens Pearson. And the reason, of course, is that somehow if curvature blows up, then that really is a proof that you cannot extend the metric C2. But to preclude the possibility that there's some other funny differentiable structure that you can define that allows you to extend as a continuous metric is difficult, because you don't have pointwise invariance. Pointwise invariance stop at curvature. So anytime you want to talk about phenomena which are less regular than curvature, it's very subtle even to capture. But in any case, this is now a theorem, and you really should think of this as the definitive statement about the strength of the singularity of Schwarzschild. It is so strong that you do not continue the metric. Okay, so that's Schwarzschild as far as this book is concerned. Let's compare with Kerr. So from the point of view of the Cauchy problem, then the maximal future Cauchy development of Kerr initial data posed on sigma is incomplete, just like in Schwarzschild it's incomplete, but it's not incomplete because it's inextendable beyond some singularity. In fact, it's smoothly extendable beyond what's known as a bifurcate Cauchy horizon. So this terminology, Cauchy horizon, is due to Stephen Hawking in one of his early papers. So the thing is that to an extent, it's simply that these extensions are no longer globally hyperbolic, so they're no longer uniquely determined by initial data. And this is a quite pernicious sort of type of Cauchy horizon, because it's not just that there is some incomplete geodesic that passes the Cauchy horizon, but all incomplete time-like geodesics in the original space-time, they live another day in the extension. Okay, so all incomplete observers in the original space-time, they can be extended at least a little bit in some extension, and these extensions are not unique. So sometimes in textbooks one sees maximal analytic extension, but there's no sort of reason from the point of view of dynamics to prefer that extension over any other extension. So of course, a similar phenomenon, as most people know, occurs in Rice-Rosen solution, which is a sort of something to keep in mind because it's an easier example. Of course, it's an electrovacuum solution, but it's strictly symmetric. And what I want to emphasize is that what this means is, in particular, the statement of Penrose's celebrated incompleteness theorem, in the context of Kerr space-time, it's not due to singularity formation, because in the context of that space-time, this is exactly the space-time to which you have to apply that. So, it really is a theorem not about singularity, but about loss of uniqueness. It really is a theorem that's saying in this context that you have a Cauchy horizon, and thus.
What do you mean by loss of uniqueness? Which uniqueness do you have in mind?
I have uniqueness of the solution to initial value problem. So the statement that there is a unique sort of motion of
And how do you lose that?
Well, you lose that as follows: that so all these extensions here, they are no longer uniquely determined by Penrose. There's not just one
There are many ways of extending. That's where
infinitely.
I see. Okay.
And you cut out singularity here. The singularity of the parametric.
Well, the sort of the singularity that we often see in the curvametric, which are these time-like curves that come from here, they have to do with a particular extension. And so there is no reason in principle why there might not be other extensions that are nowhere singular. That's not. So for instance, in the case of Rice and Nordstrom, you can write down such if you couple the Einstein equations to perfectly reasonable math. Moreover, sort of maybe there's some singularity further in the future over there, but it's not telling you, it's not resolving this issue of non-uniqueness. So somehow, in some sense, this legacy is even more important than the statement. Well, maybe keep on extending, somewhere you'll hit singularity, because even before, you have to deal with this issue.
Is it necessary to impose all boundary conditions on sigma? Can you not allow some of the conditions to involve some future time?
Well, it's a very good question, but should say, I mean, in some sense, what's missing here is, okay, you need all of a sudden more initial boundary conditions. That's essentially what's going on. But that happened dynamically. Let's say you didn't know that should happen until you go to Cauchy-Rose. So, in any case, I mean, there are many ways you could hope to try to resolve this issue, but there's certainly not a definitive. I mean, it's a problem, and sort of, in fact, and in some sense, one might think naively that this situation of Schwarzschild is much worse, right? It's certainly much worse for this observer here. I'd certainly prefer to be this observer here. Okay, my future is not predicted uniquely, but I do get to live another day in this extension.
You get into a multiverse situation.
I get into the multiverse, I find out there are lots of advantages that come out from future not being determined.
Yes. Determinism is Einstein's favorite principle. And this is not even quantum mechanics. What would Einstein react to that?
Yes. No, I mean, it's interesting because, as you said, this is a completely classical failure. And it's not a failure this failure of determinism has nothing to do with anything blowing up. So the whole point about this is that this is completely smooth. So there's no, you cannot say that, well, I've exited the realm of general relativity. Something blew up, and thus I know that I need some other principle that, from this point of view, everything is smooth. And so the phenomenon is completely global. That somehow what's going on is this global failure of the domain of dependence. You want to see more initial data, and you're not given those, but you thought you had all the initial data. This is nice, that's totally flat, complete. It is a very strange phenomenon. It is very strange, and somehow and this was to what we'll say next. Somehow it is more problematic than the Schwarzschild case, because in some sense, from again thinking in terms of classical theory, the Schwarzschild case has it gives classical general relativity a very attractive closure, because you see, whatever you think about, if you get too close here, you might reasonably think that, yes, if you want to understand the underlying physics, you need full quantum description, etc. But as far as classical observers are concerned, you don't need that description to say what happens to classical observers, because before the classical observer actually gets there, the classical observer ceases to be a classical observer. This is no longer a classical observer. From the point of view of classical observers is destroyed. So this
The notion of classical observer is very foggy. It's
True.
not really defined.
So,
What is an observer? That's a big question, right?
that's one of the reasons why I prefer the formulation of this, which puts observers out of the picture. But yeah, I mean, if we sort of permit ourselves one more minute of this sort of speculative epistemology, then somehow, and I'm just doing this to motivate Penrose's considerations for formulating the conjecture. Once we formulate the conjecture, we can throw out all the study. But just to put us all into the logic of that conjecture. The point is that, you see, Schwarzschild gives us this attractive closure for classical theory, that if you only ask classical questions about classical objects, you don't need to know what actually happens when you're exactly here. Whereas the situation in Kerr is very unattractive from this point of view, because this is a completely classical process. Observer is completely classical, remains classical, but classical theory does not say what happens to him or her after they cross the Cauchy horizon. So in this sense, the Kerr situation, which naively is much more favorable, and certainly much more favorable for the observer themselves, is much less favorable for epistemology, at least if you like this notion of a closed, in that sense, classical. Okay, so this is what motivated historically the strong cosmocensorship conjecture. So this was Penrose's way out of this conundrum. And basically his conjecture was the statement that Kerr is a fluke. And that yes, the situation happened in Kerr, but Kerr is a very symmetric solution. And if you had any sort of generic asymptotically flat initial data, and you looked at, the maximal future Cauchy development, so that is the part of the space-time that is always determined from initial data, you cannot extend that further. So that was Penrose's hope, that if you add genericity assumption, you can kill this phenomenon completely. Now, when I say it's inextendable, okay, to make this precise, I have to say inextendable as what? So we already sort of discussed two notions of inextendability. And it's clear that if you want this sort of to really mean determinism in the sense that we said, that sort of classical observers are destroyed, and if you believe that that really is related to inextendability as a C0, as a continuous Lorentzian metric, then the way you would want to make this conjecture is that generically, for generic initial data, that's to say the part of the space-time which is indeed uniquely determined cannot be further extended, even merely as a continuous Lorentzian.
But 5 minutes ago, you told us it is extendable. So in what sense was it extendable before?
I said that Kerr is extendable. And so for this conjecture to be true, in particular, Kerr has to be severely unstable. This is saying for generic. So not for every, but for generic. So that says that the set of initial data for which this is not the case, which, as you said, includes Kerr initial data, should be exceptional within the moduli space of solutions. So that is the statement. So this formulation, again, you should think of it is basically saying that the Schwarzschild situation, which of course it's sort of funny, you can think of Schwarzschild as a special case of the Kerr family. Schwarzschild, of course, is manifestly non-generic within the Kerr family, right? It's the A-0 case of the Kerr family. But this would say that the Schwarzschild behavior, which is non-generic in the Kerr family, if you go to the full modular space of all dynamic solutions of the Einstein vacuum equations, it's again generic. Okay. So this is the hope. So before talking about the status of this hope in lambda equals 0, let me tell you about another aspect of Kerr. So it is widely believed that the Kerr family in the exterior is stable. So as I just said, if we believe this conjecture, it has to be severely unstable in its black hole interior. Exterior. So that just means that wiggle current data, ever so slightly, you evolve the Einstein equations, the exterior region should look like Kerr, and actually the space-time should settle back down to Kerr, and okay, there are two ends, it will be actually two illusions. So this isn't quite proven yet in mathematics, but actually this is something that one can in principle now prove, or hope to prove in the full sort of sub-extremal range of parameters with ideas which are on the table. So in particular, the Schwarzschild version of this conjecture has recently been Rodniansky and Taylor. And in principle, one can hope to extend this to the full nonlinear stability of Kerr in the full sub-extremal range of parameters. And actually, there are many others who also contributed on this problem, mathematics, in sort of recent years. Let me not discuss all that literature, because that would take me vastly afield. But this is not a contentious conjecture at all. This is something that certainly, sort of if you accept anything about what astronomers interpret sort of classical astrophysics, then you implicitly have accepted this conjecture. So I'm going to accept this conjecture, okay, and tell you immediately what it says about the previous conjecture in the black hole interior. Because that's a theorem from a few years back with Jonathan Luke. So we actually showed that if Kerr is indeed stable in the black hole exterior as conjectured, and as I said, as in principle should be proved, then actually its Penrose diagram is globally stable. So in particular, not only actually is its Penrose diagram globally stable, but the metric again extends at least continuously across Cauchy horizon. So that means that observers, classical observers, can escape maximal Cauchy development unscathed in the sense that we said before, that's to say, not torn apart by infinitesimal deformations. So as a corollary, if Kerr is stable in the black hole exterior, then actually this C0 formulation, strong cosmic censorship, is false, cannot be true. So that's a problem. So back to the drawing board. So here was sort of the template for the conjecture. So we cannot fill this conjecture in the strongest possible sense that we would like to, which would have given us the most definitive resolution of the sort of issue of determinism. So let me weaken the conjecture. It's still called strong cosmic censorship because the strong is trying to differentiate it from something which is completely different in reality. So let me not try to explain the etymology. So I'm going to weaken it by requiring something more of the extensions. Not only should they be continuous, but their Christoffel symbol should be locally squared. So you should think, morally speaking, that this statement is weaker than the statement that the metric be in C2. So it's something between the statement that the metric be twice differentiable and that the metric be merely continuous. So
of all things you could integrate, Christoffel symbol is the worst. It's not gauge invariant.
But this statement is a gauge invariant. Exactly.
Integrable of Christoffel is invariant?
Yes. So the statement that the manifold is inextendable as a manifold with locally square integrable Christoffel symbols. Well, I mean, in general, remember that the value of this integral for any given coordinate is not gauge invariant, but the finiteness of the integral you should think of that as a gauge invariant.
Why can't it be a gauge artifact? I mean,
again, this is a way of imposing. This is a way you should think of this as a way of imposing your atlas. Sort of again, and sort of any given coordinate system. The value of this can be different, but sort of a set of coordinate systems for which this is finite, okay, define a notion of an atlas in this regularity class. I mean, it's similar with, the issue of the C0 Lorentzian or any sort of any regularity class. So
It has analog in Young-Mills theory, this concept. In Young-Mills gauge theory, is there a similar concept?
Certainly, yeah.
Have you ever seen such a concept?
Well, you could certainly introduce it. Yeah, I don't know if this has been. Well, I mean, what I can tell you is sort of what is the motivation for this formulation. So this is sort of the strongest formulation, which is still compatible with what we actually proved in the theorem. But more importantly, and this will explain the origin of the sort of and an analog, which, if you want, I hope motivates sort of why one would consider this in particular. So in general, for the class of nonlinear PDE for which the Einstein vacuum equations sort of belongs, you can consider a more general class of solutions known as weak solutions. And there is a big sort of tradition in, let's say, to give an example of a PD which is very similar. If you look at the compressible Euler equations of fluid mechanics, and again, it's sort of a system of quasi-linear wave equations. You can write it very much like the Einstein equations. And we know, in fact, that the right physical solution to consider is not the smooth solutions, but it's the weak solutions. And the reason we know that is because even if you start with smooth initial data, then sort of generically you have what's known as shock formation. So certain discontinuities in derivatives develop dynamically. And yet there is a unique solution which continues. And that solution is a weak solution. And it is in precisely this sort of class. That's to say the derivatives of the field. And here the field is sort of, you have to write the equations in a way that it's a system of wave equations. If you write it like that, the derivative of the fields would be locally squared. So somehow this, and moreover, you can interpret the PDE under these assumptions. So you can, in fact, interpret, it's non-trivial, but you can interpret the Einstein vacuum equations for metrics in this regularity. So even though there's no such thing as curvature in this world, but you can still write down the Einstein equations in the appropriate. So in any case, this is the sort of strongest form of conjecture that may still be true. And the nice thing about this is that were it true, it would really tell you that, there is no solution of the Einstein equations beyond this Cauchy horizon. Even if by solution of the Einstein equations, you mean a weak solution. You mean the kind of thing that you would be considering, let's say, in fluid mechanics. Okay. So this would really say that at least at the level of a PDE, you have determinism. There's really only one solution of the Einstein equation. So,
well, certainly with some assumed symmetries and so on, right? You're talking about Kerr solution.
I'm not assuming any symmetry.
Oh.
The whole point is that this is generic asymptotically flat initial data. So the moduli space of initial data is an infinite dimensional space. There are no symmetries. There are no symmetries, and in this theorem, there are no symmetries here. So this theorem is a theorem about the full equations without any symmetries. Okay. So so that's the sort of, if you want, the status quo as far as lambda equals 0 is concerned. So the strongest version of strong cosmic censorship that would have given, would have allowed us not to have this debate at all, because it's really definitive, is not the case. This is in some sense the best thing that might still be true. This is an attractive conjecture. It gives some notion that the theory is deterministic, but certainly this discussion we just had is very useful because, unfortunately, given that one can still ask, is this really the right statement? Is it something else? What is the right notion of solution, etc. Okay, I don't have a better answer than what I said, which is to a large extent by analogy. In any case, this formulation, which I'll call just a little formulation, is now, we'll see, been sort of discussed a lot in the literature in recent years. And we'll anyway, I'll come back to all of this in more detail when I talk about what I really want to talk about, namely the lambda not equal to zero case. Okay, but there's still something that we have to do before we get to the lambda not equal to zero case, is I have to tell you why the status quo is the way it is for lambda equals zero. Okay, I have to tell you why that conjecture, its strong formulation is not true, and why we can hope that this conjecture is true. And it turns out that the underlying mechanism involved in both of those statements, the disproof and the remaining conjecture, is really a statement of competition between blue shift and dispersion. So of course, as we just discussed, all those theorems and conjectures, they really are about the full nonlinear Einstein equations without any symmetry, etc. But fortunately, you can sort of understand what's going on at the linear level. And I'll return back to how fortuitous that is in a posteriori. You can understand this problem at the linear level, and the understanding is correct somehow. So let me say, what is the linear analog of this problem? So the linear analog, for simplicity, is just the following. So let's fix Kerr, or maybe even Rice-and-Rodsum if you want something simpler. So this is now fixed, and just consider linear fields here. And again, what you really should be doing is linearizing the Einstein equations. But again, for simplicity, let's just consider the linear wave equation. So what you need to understand at the linear level is, you start for initial data here, for instance, compactly supported or something like that. And you really want to understand what is the behavior in this region. In particular, what is the behavior here? And I claim that if you understand this well enough, then if you're well versed in the techniques of nonlinear analysis, you can hope to promote that to an understanding of the full nonlinear Einstein. Okay, but let's forget about the full nonlinear Einstein equation. Let's just take this problem.
What was the significance of the psi naught and psi 1? The naught and the 1?
Oh, this is just because this is second order.
Oh, so those are
you need two pieces of initial data.
big and okay.
And it's derivative, exactly. Okay, so one of the characters that plays a role here is the famous blue shift instability. So again, this was first discussed by Penrose. In fact, it was discussed precisely as a justification for his initial conjecture of Stronghold and censorship. So the story we all know, so you have two observers. So it's, I don't know, Chris and Mihalis. And Chris is all very conservative and all that. And so safely stays outside of the black hole, and Mihalis jumps right in and goes straight to the Cauchy horizon. And Chris, sort of nice, he sends me an email every year, news. Well, as we all know, all those emails, I receive them at smaller and smaller time intervals. So I'm completely inundated with these emails that are shifted infinitely to the blue. So that sort of suggests that there's some instability associated with the Cauchy horizon. And of course, okay, if you believe that, the Einstein equations, or this wave equation that I wrote down, will see this effect in the geometric optics sort of limit, then this should create something bad for solutions of that Cauchy problem for the wave equation. So that's sort of the thing. And well, Penrose's sort of intuition went further. Of course, for linear theory, you might say that, well, the worst thing that can happen for a linear equation is something bad in the boundary. A linear equation cannot blow up here. That's sort of very general theory. The worst thing that can happen for a linear equation is it blows up on the boundary. But then you might think that, if the linear equation blew up on the boundary, then nonlinearities would kick in a little bit before. So that's why the original expectation was that you should have actually a space like singularity strong in the sense that we said. Okay. So okay, so that's all great, but there is a sense in which that heuristic is competing with something secret. And the reason is the following. You see, the way I said this heuristic, Chris sends me an email, every year, and the email is of the same strength, it's of the same length. Okay, but that's not what happens to waves over here. Waves over here, they actually disperse. So in some sense, the first thing you have to really understand is how do waves disperse in the exterior? And this again is something that in the physics literature goes back a long time, in particular the Schwarzschild case to work of Price. But only recently, or relatively recently, have there been definitive theorems that say that indeed, this is her case in the full subextreme regime, solutions to this linear wave equation do indeed decay as you go there at sufficiently fast rates. And so the definitive theorem is the one written here. And the statement, the only thing that's really important to remember is that these decay rates are inverse polynomial. So these decay rates are inverse polynomial. In particular, they're inverse polynomial along the event horizon. So, anyway, and I should say many people have contributed to this over the last 15 years in mathematics literature. I don't have time to do justice to everything. So that's great, but this in principle competes with the blue shift of this decay. So you might worry that this decay could kill the blue shift, but actually you need not worry. So it turns out, again, this is a relatively recent theorem, but it goes back to sort of heuristics that have been around for some time. But now it can be definitively stated in this context that if you look at the generic solution of the wave equation, then despite this decay in the exterior, you still have this blow up at the horizon. What is blowing up? What blows up is the local energy of C. And what is the local energy? Sorry for these disregard them. It's just you go to local coordinates at the Cauchy horizon, okay, and you look at the derivatives of C, and you integrate in a little region the derivative squared. So that's really the energy that would be measured by a local observer. That blows up. Okay. So, so those are the. So this is the theorem, and maybe I should say that this theorem recently also for linearized gravity.
Is this the same phenomena that one observes in Hawking radiation? This blue shift of modes.
Well, certainly let's say the blue shift that you see in the Hawking calculation is analogous to this. Of course, that's the blue shift of the event horizon when you look at it backwards, whereas this is the blue shift at the Cauchy horizon. But it's as such, it is indeed very analogous. Yes. Yes. So okay. So there is this blow up at the linear level, and in fact, very recently, maybe in the past few weeks, this sort of type of blow up result at the linear level for the derivatives has been obtained.
Question in the chat.
Oh, there's yes.
And he asked that the blow up of local energy of the psi imply a singularity used non-conservation.
Does it imply a singularity?
Imply a singularity induced non-conservation.
So okay, I'm not sure I understand the last part of the thing. So this is certainly, you can think of this as a singularity of the solution. Okay, and again, I'm telling you exactly what is singular, what is blowing up. It's derivatives of C squared integrated. So it's the energy of C is blowing up. Now, if because you mentioned the word conservation, so remember, in the black hole interior, there's no conservation of energy. So if one is surprised, how is the energy infinite? The energy certainly here is finite. Well, there's no contradiction to that, simply because energy finite here does imply that the energy in the exterior will remain finite, but it doesn't imply something about the energy in the interior, and certainly not about the local energy at the Cauchy. So, okay, but at the same time as this sort of statement about singularity, there's another theorem, which in some sense at first instance is more surprising given the fact that we know about this blue shift instability, which says that the amplitude of C remains bounded. So the amplitude of C itself remains bounded, in fact, continuous. So the generic solution of the wave equation on this background Okay, and this is again Kerr, Rice, and Rodstrom, full sub-extremal range. So the wave equation, coming from sort of smooth, nice initial product, the local energy will be infinite around every point of the Cauchy horizon, but the amplitude itself will remain downward. And if you want the full sort of nonlinear, so my theorem with Jonathan Luke, where we showed that the metric in the full nonlinear theory is continuously extendable beyond the Cauchy horizon. Well, this is a vast generalization of this theorem. And you should really think that in some sense, C, you should think is like the metric itself. Derivatives of C, that's like Christopher's.
So is this psi necessarily linearized gravitational field, or it could be any gauge field, like electromagnetic?
So in this, well, in the statement of this theorem, this is actually just a linear scalar field massless. So this is really, the simplest such example.
But then the question arises, how do you couple to gravity, minimal, conformal, what is in this operator?
So there's nothing, this is minimum here. Now you can certainly, try to formulate this theorem in more general settings. And as I said, again, this actually applies for the full vacuum equations. So, I mean, in some sense here, when I'm not thinking of this as matter, I'm really thinking of this as a model in place of the linearized gravity, and not as a matter that I want to put on the right-hand side of the Einstein equations. So this theorem per se, on its own, doesn't say anything about the Einstein vacuum equations. But I claim that our theorem about the full Einstein vacuum equations is sort of very similar. It's fine. And this model, really the simplest thing you could write down, does actually capture what's going on as far as this. And so this extrapolation, from this equation to the full Einstein equation, where you think of C as being the metric and derivatives of C as being the Christoffel symbol, I claim is reasonable. And that's why it's reasonable to hope that this theorem, will eventually allow us to say that the conjecture is true, at least in the neighborhood of the Kerr family. So I want to make one other point, that strong cosmic censorship is a very ambitious conjecture, because it's really telling you something supposedly about the generic solution in the moduli space of all solutions. To disprove a version of strong cosmic censorship, it suffices to find a window in moduli space, an open set in moduli space for which the statement is false. So, disproving, let's say, strong cosmic censorship in the C0 formulation really just meant promoting this theorem, the theorem about the full Einstein equations around, in the neighborhood, when you're always looking in the neighborhood of Kerr. But let's say, if you want to promote this statement to a proof of, whatever formulation of strong cosmic censorship, it's not enough to look at a neighborhood of Kerr, because, you can have things which are very far from Kerr. So, so that I think will take many, many years to do. But what's more reasonable is if one could at least say that in a neighborhood of Kerr in the moduli space, the statement is true. And that's something that I think in the next few years, people will be able to do on the basis of what's in here. Okay. So one last point, just to summarize what happened at the linear level. And this will allow us to make comparisons now for the lambda non. So you have this exterior dispersive effect, which is polynomial for psi. Okay. But fortunately, in the right coordinates, the blue shift leads to sort of exponential growth of derivatives in the right coordinates. And somehow this exponential beats polynomial for derivatives. Okay. So that's sort of what happens. So the exponential beats the polynomial for derivatives. So that says that the derivatives do blow up. So you have indeed this type of blow up, but it is not strong enough to destroy the amplitude. So this growth, right, is not strong enough to make the amplitude of C. Okay. All right. So now let's go to the sort of topic proper of this talk, namely strong cosmic censorship versus lambda. Okay, so what happens when you turn on lambda? So First of all, sure, most people know here that Kerr family has its cousin solutions. When you turn on lambda, the Kerr de Sitter and Kerr ADS. This is the precise form of the metric. So these were first worked out by Francis Carter. We won't need the precise form of the metric in what I say. So let me first talk about the Kerr de Sitter case. So this is the Penrose diagram of Kerr de Sitter. It's more complicated than Kerr because you have these cosmologically expanding regions also. Okay, so this is the black hole interior, and the things to notice is that, well, it's still bounded by a Cauchy horizon, and you have all the same considerations about a Cauchy horizon that you had for the Kerr solution. And you can think of this region here as the analog of the exterior region. Okay, so the analog of the exterior region is a region now which is bounded by two horizons, say an event horizon and something like a cosmological horizon. So first of all, let me tell you the good news about the lambda greater than 0 case, which is the following. Actually, the sort of considerations in the exterior region are significantly easier than in the exterior region of Kerr. And the reason is precisely that this region here is spatially compact. And because it's bounded by two horizons, for reasons that I don't want to discuss in too big detail now, you actually expect exponential decay of perturbations. And the faster you expect perturbations to decay, the easier it is to prove nonlinear stability. And so in fact, it's several years now, there's a remarkable, fully sort of nonlinear result, which says that this triangular region here is nonlinearly stable for Kerr de Sitter in the case where the rotation parameter is very small. Okay? Now, remarkably, in the case where the rotation parameter is not very small, even the modal stability of Kerr de Sitter is an open problem. So the sort of even linear modal stability, which is a completely ODE statement, is open. So that was the statement that Whiting famously proved back around the late 80s in the Kerr case. Okay, so that statement in the Kerr de Sitter case is still open. But in the very slowly rotating case, at least, it's true. And in fact, you have this remarkable full nonlinear theorem due to Hinson bias. Okay. So in view of this theorem, my theorem with Jonathan Luke about the interior applies more or less without a change. So in particular, a corollary of this, of the theorem of Hinson bias and my work with Jonathan Luke is that the C0 formulation of strong cosmos censorship is equally false in lambda greater than 0. And now this is not conditional on any nonlinear stability because the result exists. So the interesting question to really ask in the lambda greater than 0 case is what happens with the Lulu formulation? Should we still expect this to be true? And here is this funny thing with numerology. See, as I said, the reason that stability here is easier is precisely because you have exponential decay. And recall that blue shift meant in whatever coordinates exponential growth. So now the competition between dispersion and blue shift is really a competition among equals. And it's not clear a priori who wins. And there's some naive ways of looking at the numerology, which depend on various things. And well, I looked on that a few years ago in a very naive way, actually, but in any case. And so I made the following conjecture that, so let me first give a fully nonlinear version of this conjecture, but which was restricted to symmetry. And so, well, in symmetry, what's the analogous problem? Well, look at Reiser-Nordström de Sitter in place of Kerr de Sitter. So again, the Penrose diagram is similar. And now couple in a scalar field, minimally, let's say, or something like that. It's the simplest thing that allows you to have a fully nonlinear strictly symmetric problem. So this is a much easier type of problem. So what I conjectured is that there's a window around extremality for which the Christodoulou formulation will fail. So what I conjectured is that if you have, so this is in a fully dynamic solution, if you have a black hole event horizon, which is sub-extremal, but only a little bit sub-extremal, there's a precise sort of window that you have, then you should expect that the Cauchy horizon is more regular than in the lambda equals 0 case. In particular, is regular enough so that you can, in fact, extend the solution not only as a C0, not only as a continuous metric, but as a weak solution of the system. So that was my conjecture. So if you believe that, then even this Christodoulou's formulation of strong cosmic censorship is false in lambda greater than 0. Because all I need to find for you is an open set in the moduli space, which falsifies the predicate. So there's been some work, actually, some analytic work on this model further. This conjecture in this form still has not been proven. So there's a linear version of this conjecture that we can make also in the Kerr case. So maybe this is easier to understand. So the statement would be that on a sub-extremal Kerr de Sitter or Reisner-Nordström de Sitter with parameters sufficiently close to extremality, then if you take any solution of the wave equation, okay, then the solution will extend as a weak solution. That's the conjecture. So let me stick to this linear version, because here there were some very exciting developments. So, in the Reisner-Nordström case, then evidence has been provided in favor of the above conjecture in this paper from 2 years ago, which attracted a lot of subsequent work. So this paper, again, is actually a mixture of some actual mathematics and some very nice numerics. But maybe surprisingly, especially to me, actually in the Kerr de Sitter case, evidence has been provided for the failure of the above conjecture. So the thing that determines the numerology of decay in the Kerr de Sitter case is actually different than in the Reisner-Nordström de Sitter case, and different from what I had expected. So, so interestingly, in the Kerr de Sitter case, it seems that for all sub-extremal values of the parameter, you should have blow up at the Cauchy horizon in H1 log, as we would say in mathematics, so the local energy law. So if you believe this, then it's sort of funny that it means that strong cosmic censorship, now I'm extrapolating to the full nonlinear theory, strong cosmic censorship would be true for the vacuum equations, but not for the electrovacuum equations. So, well, that you can interpret in various ways. That the world is vacuum. I believe in strong cosmic censorship, thus the world is vacuum. But you might also interpret it as saying that no, I mean, strong cosmic censorship, if it's a physical principle that's to hold, it should hold, equally well for any reasonable Einstein matter model. And so if it doesn't hold for the electrovacuum equations, then that's a problem. So, so again, sort of back to the drawing board here. Is it really the case that strong cosmic censorship in this crystalline formulation is gone if you add a positive lambda? So actually, with a collaborator, Jakob Stjapin-Hoffman, we found another sort of way out to keep strong cosmic censorship. That's actually a very general theorem that you can make. So our theorem, basically, the logic of it is the following. If the motivation for wanting to consider weak solutions of your equation beyond the Cauchy horizon is you believe that physical solutions are the weak solutions, then you should certainly also allow them in initial data. That's to say, you should allow your initial data to be in the exact same class as sort of the extensions that you allow. Because, before we were always considering smooth initial data, but we were allowing weaker extensions. And a beautiful symmetry sort of happens. And the statement is the following, that if you consider generic initial data in this H1 log class, so that just means I consider generic initial data with the property that the local energy is finite. And again, as I said, you can easily interpret solutions of the wave equation in that Cauchy problem. You have well posed all that in that class. And in that class, the generic solution will not have that regularity. And in fact, it's sort of there's a symmetric sort of formulation. You tell me any analogous regularity. You tell me that I want to look at the class where 10 derivatives of the solution are locally square integrable. Then in that class, the generic solution will have the property that 10 derivatives of the solution are not square. And it's very remarkable that you have exactly that statement. And this really has to do with a funny relation between the surface gravity of the event horizon and the Cauchy horizon that happens to always obtain in these solutions. That's what governs this statement. So anyway, what this tells us is that you can in principle save Stronghold from censorship by enlarging the class of admissible initial data, keeping the statement about what extensions you allow the same and enlarging the class of admissible. Okay. To sort of tell you what's going on here and why this happens, you see, when you look at rougher initial data, your decay in the exterior is no longer governed by quasi-normal modes. It's governed by something else. And that's why the numerology becomes. Okay. So actually this was further developed by Oscar Diaz, Harvey Real, and George Santos in a paper, and I like the title, sort of motivated by this idea of generalizing to rougher initial data. So taking the rough. Okay. All right. So in the remaining 4 minutes, I'm going to talk about what to me is the most interesting, just maybe on account of how surprising it was to me, case, namely what happens to these considerations when you add a negative cosmological cost. So when you look at Kerr anti-de Sitter. So this is the Kerr anti-de Sitter spacetime. Again, there's a Cauchy horizon as in Kerr. And of course, again, in this problem, the first thing you have to understand anything about what's going on here is what happens in the exterior. And now, as we discussed at lunch, if you look at this problem in the ADS case, you're looking at even just the linear wave equation, but everything I say about ADS will be about the linear wave equation. Then you, of course, have to impose boundary conditions at the boundary, at the ADS boundary. And so everything I'll say will refer to reflective boundary conditions. So under that assumption, it's a theorem of Holtzigel and Smilevici from back in 2014 that solutions of the wave equation with sort of smooth initial data here and reflective boundary conditions will decay on the event horizon to 0, but the decay is only inverse logarithmic in time. Okay, so remember, positive lambda, exponential decay, 0 lambda, polynomial decay, negative lambda, inverse logarithm. And this is sharp. That's to say that the generic solution in the appropriate class will decay like this and no faster. So what does this mean for the interior? All the work about the interior was predicated on the fact that at the event horizon, you had at least polynomial decay, in fact, at least polynomial decay of some rate. So actually, upon thinking about this, my original expectation was that the interior will be always much worse, the interior behavior. And in fact, my expectation was that C would blow up in amplitude because of this difference. Okay, so that's what I thought. So could C now blow up on the Cauchy horizon? I thought it would. I thought it always would. And again, to return to this sort of picture to have in mind, logarithmic decay of C, exponential growth of derivatives at least due to blue shift. Exponential seems to really eat up logarithmic. So maybe the amplitude is now. So that's what I thought, but one of my then students, Christoph Kehle, proved me completely wrong. So he looked at the Reisner-Nordstrom anti-de Sitter case, okay, and all the considerations so far are the same. Took a look at Reisner-Nordstrom or Kerr, and what he showed is, despite the slow decay on the event horizon, it's just as before. That's to say, solutions still are continuously extendable beyond the Cauchy horizon. And well, the proof is very, very different, exactly because you cannot exploit what was being exploited before, namely the polynomial decay. Okay, so he showed that, but then it got very interested. So then he looked at the Kerr antidecitor case, and the natural thing would be, okay, to now prove the same thing for the Kerr antidecitor case. And here he discovered something very new, very unexpected, which is the following. In the Kerr antidecitor case, the question of the blow up or not of psi and amplitude depends on the parameters. And as we'll see in just a second, it depends on the number theoretic properties of the dimensionless versions of the parameters. So what he showed is there exists what's called in mathematics a bare generic set of black hole parameters. So it's sort of funny, this is not generic in the traditional sense. In fact, as we'll see in a second, the measure of this set is 0. But it is generic in this other competing topological sense called bare genericity. So he shows that there is such a set of parameters such that if those are the background parameters, then the generic solution of the wave equation on that background will blow up in amplitude. So what this means is that the original formulation of strong cosmos censorship, at least if you're willing now to adopt this bare genericity, is true in the negative cosmological constant case. Okay. At the same time, he conjectures that in the complement of that set of parameters, then, so this is not yet a theorem, but conjectures that in the complement of this very specific set of parameters, then you have boundedness of psi. But of course, it is not uniform in the sense that as you approach those bad parameters, things will blow up. But in some sense, the interpretation of this conjecture would be that in the Lebesgue generic sense, zero formulation is, again false. So somehow the C0 formulation in the lambda less than 0 case now depends very much on this notion of genericity. So let me very briefly tell you what happened, and then essentially the end. So remember that here you have this logarithmic decay. So the reason you have logarithmic decay, one way to understand it is governed by slow quasi-normal modes, by quasi-normal modes that approach exponentially the real axis. Okay, so it's the totality of those modes. If you fix one mode, you don't see logarithmic decay. Any one mode decays exponentially. But if you sum over all modes, that sum decays logarithmically. And now the funny thing is the following. So there's a scattering pole associated to the interior scattering map, which in the Reiser-Nordstrom case is at 0 frequency, but in the Kerr case is in a frequency which has to do with rotation. And so if that frequency is just right, then that frequency can be in resonance with the totality of these bad modes. And that's exactly sort of what happens. And if you think about it, what it means, if you do the calculation, means that the black hole parameters satisfy what one can think of as a generalized non-Diophantine condition. That means that the dimensionless parameters are sort of essentially are approximated too well by rations.
How can one frequency be in resonance with the totality of modes? Maybe I misunderstand the definition of dispersion.
Yeah, so no, it's a very good question. So it's not, so in reality, this is not one frequency. So the poles are again, it's a sequence of frequencies in the in the rotating case. So what one should think is that you have a pole when omega minus a fixed number having to do with rotation times the azimuthal frequency is equal to 0. So it's a whole sort of sequence of numbers depending on the azimuthal. So that's somehow in the non-rotating case, it's just a pole at omega equals 0. And of course, omega equals 0 has nothing to do with these, these quasi-normal modes, which are in the limit as omega goes to infinity. It's a very good point. So, so this is really this generalized non-Diophantine condition. If you know about Diophantine analysis, then you sort of remember that this is precisely the set of such numbers is bare generic, but non-generic in the Lebesgue sense. And in fact, this is reminiscent of small divisor problems in classical mechanics. So this is exactly the type of conditions that were studied long time ago, starting from work of Laplace and others. So these are exactly that phenomenon from the stability of the solar system, which again are it's exactly for that reason that you have this strange mixture of stability and instability in the problem of stability of the solar system. You see something very similar here. So so let me just leave you with this quote from Christoph Paley's thesis. So he says, in this sense, the fate of observers falling into such black holes, though bleak, is determined, answering the linear scalar analog of the Stronghold censorship conjecture in the affirmative. That's to say, in this bare generic sense. Thus, surprisingly, small divisors and Diophantine approximation, the villains of the stability of the solar system in Newtonian gravity, may turn out to be the elusive cosmic censor which Penrose was searching for in order to protect determinism in general relativity. We see in our results that the pervasive nature of instability in dynamical systems can sometimes be conscripted to do good, a vindication, perhaps, of Poincaré's faith in instabilities caused by small divisors. Okay. So, so in summary, the jury is very much still out in who wins in this competition. Thank you very much. Sorry.
I'm just curious if this thing is informed by the gigantic body of work in deterministic chaos, where the presence of small denominators is one of the standard routes to chaos, the breakdown of the Tori, invariant Tori, etc.
Yes.
So it's, of course, gigantic amount of mathematics
Yes.
developed for that.
Yeah, and I mean, this is analogous exactly to that. And I'm sure that techniques that have been developed there will be very useful. I mean, first and foremost, okay, one wants to understand what happens at the nonlinear level. As far as the lambda less than 0 case is, then everything is as far linear. And of course, there are all sorts of things that happen because precisely, that could indeed lead to much worse things at the nonlinear. But so yeah, I mean, I think Christoph and whoever else is pursuing this, I think they have a lot to absorb from that position. What's really remarkable to me is that this had not been noticed. That it is something that at the heuristic level, what's said here, he proved the theorem, but moreover, he discovered this connection, which is very non-obvious to me. I don't think it had been noticed, or even there could have been such a thing going on. So anyway, I think there's also a lot more to try to understand at the heuristic level. It's a really, if anyone's interested in these type of issues and likes quasi-normal modes and that type of thing, this is a great question to look at, because it's it really, there is no, in the lambda greater than 0 case, this paper here, already has hundreds of citations, and they became an industry to look at this numerology in the lambda greater than 0 case and what happens. There's been a lot of work. I think this case is even more interesting, the lambda less than 0 case, and there's just this. I think it's a good thing to look at. Yeah.
Aren't Diophantine type equations bound to be destroyed by quantum effects, quantum corrections?
Well, I mean, even, okay, obviously, what happens at the quantum level is okay, anybody's guess, but even let's keeping to the classical level, but nonlinear. When you perturb this space-time, you look at nonlinear, you no longer have a fixed background. So the background is evolving. And as it's evolving through, you know, a continuum of reals. And any continuum of reals will contain both, you know, the non-Diophantine and Diophantine numbers. So
You have Diophantine conditions, the integer involving solutions that must be integers,
well, I mean,
or
it's
not?
sort of it's generalized non-Diophantine because the role of the integers is played by the sort of real parts of the quasi-normal modes. So there's the sequence of quasi-normal modes.
They're real numbers, they're not integers.
So they're not quite integers.
Okay, then, all right.
They're real numbers, but somehow in the limit, they approach the sequence of integers, basically,
Huh.
or you know something. Their spacing will be integer.
Those are not associated with conserved charges or anything like that, those integers?
Well, so these integers, what they are related to is actually sort of funny. So so the integers, they are related to the Lyapunov exponents of, so in the let's say lambda, so in the lambda equals 0 case, which I know better, so maybe let me talk about that. Of course, in that case, these modes do not approach the real axis, they remain a fixed distance. So there's a spectral gap. But the real part of the modes, so it's a sequence which in the limit, as you go to infinite frequency, is sort of integer spaced or something fixed constant space. And that constant you can relate to the Lyapunov exponent of the trap null geodesics. So somehow that's, you know, so it's really something about, because remember, this is a high frequency behavior. So it's really something about, you know, geometric optics. So it's something that you can relate to the underlying geodesics. So, yeah, and of course, again, you know, proving these types of statements means, okay, you have to indeed capture all those statements, make them real. But sort of the, I mean, you know, interpreting something, sort of extrapolating from your question, but you know, even staying within classical theory, but no longer linearized, you have to deal with this issue that, you know, this is an evolving solution and it's evolving through parameters which are of both type. And so, you know, if you're a pessimist, you might think that, well, you know, anytime you have an instability, that will win somehow. But it's not necessarily the case.
I think you're still lucky if like this kind of CAM theory still applies, then your system is almost integrable everywhere except the small vicinity of those, you know, separatresses, if you want.
I mean, what if you're an optimist, then, I mean, what you're saying could very well be the case. And you're exactly right that in KM, the whole point is KM successfully promotes this to a full nonlinear statement. Okay. Now, of course, wave, you know, these type of wave equations are sort of worse in some sense than ODE, but you know, it certainly could be the case that, you know, this whole picture, as stated, you know, goes to the nonlinear. But I mean, again, it'd be very nice. Unfortunately, if you want to study this problem numerically, then, you know, unlike some of these features in the lambda greater than 0 case, where, you know, there's a spherically symmetric problem that, you know, captures the phenomena. Again, you could have a slightly different answer, as we saw, but at least it's of a similar spirit. Here, this really is fundamentally a non-symmetric thing. That's to say, this phenomenon, you don't see it in the Reiser-Nordstrom case, exactly because the resonance in question is only allowed. So unfortunately, if let's say you wanted to look at this problem in a full nonlinear setting, in some model, you know, looking at, let's say, the Einstein equations in spherical symmetry with some nice matter is not a way to do it. So yeah, I mean, it would be very interesting to have some numerical evidence about what happens in a nonlinear setting, but it seems difficult.
Have you thought ever about higher dimension?
So in some sense, of course, in you know, let's look at the lambda greater than 0 case, which is the one which in some sense is most susceptible to subtle changes in numerology. So one of the reasons that there were so many follow-up papers to this was that it's very well balanced, and so adding more different matter fields, different things like that, sort of can change the numerology. And I think there have even been people who looked at higher dimensions, let's say, and again, in principle, the precise numerology can change, and that could make the difference as to whether you have this window or you don't. And so somehow in my work with Jonathan, let's say, on lambda equals 0 case in the full nonlinear Einstein equations, I think it's rather robust to, let's say, in particular, given an understanding of the exterior, then what we do in the black hole interior doesn't really depend on the dimension. So I think what we do basically would hold in higher dimensions. But sort of, these things here, it's quite, in principle, it can be quite subtle, and any change, any new parameter that you have that could change the story.
In odd dimensions, for the rotating black holes, you can have a simpler situation. For example, 5 dimensions, where now you have 2 rotation parameters, but if you set them equal, then the metrics have a lot more symmetry. I wonder whether that could provide easier rotating metrics to work with than the 4-dimensional.
Oh, that's interesting. I mean, especially numerically.
Yeah, right. Because it would be homogeneity 1 instead of homogeneity 2 in that case.
Yeah. So in general, the terminology is confusing, and because I'm not an expert, unfortunately. So if Christoph here, he could obviously answer much better. But basically, the non-Diophantine condition is the statement that your real number is not too well approximated by rationals. So it's a statement that there do not exist an infinite sequence of rationals, such that the difference of the real number with the rational decays fast with respect to, let's say, the denominator of the rational. Okay. So it's some condition like that. So it's a condition on real numbers. Now, why does it appear here, and why does it appear in, let's say, stability of solar system? Well, again, this is sort of, when you perturbatively try to solve the n-body problem, you'll get sort of denominators that have to do with, let's say, the relation of the periods of the various planets. And so, if those are too close to rationals, I mean, it's sort of intuitive also that, if you have periods which are related, which are sort of, whose quotient is a rational, that means that after some number of one period and some integer number of the other period, the planets align again. So that sort of suggests that whatever perturbation is done, is cumulative, because you have some, if you had some finite perturbation, if things come back to the same configuration, then this will just build up. Okay. So if you have exact, rational relations between the periods, this suggests that you have instability. And now, if you write down analytically the sort of perturbation formula, then it's bad, not just if it's exactly rational, but if it's too close to the rational. So that's why, sort of in perturbation theory, sort of the conditions on, let me say, the periods and whatever parameters you're using to be non-Diophantine comes up. And then it's sort of similar here in the sense that, again, it's, if you understand, there's a resonance that takes place between, if a certain sequence of numbers sort of coincides with, another sequence of numbers, that you have this resonance. But it's not just if they coincide, it's if, they are too close. Okay, and sort of this non-Diophantine condition is what captures this being too close. So that's sort of the rough answer.
Good question. So let's thank you.